All right. Good evening, guys. I hope you guys can hear me. And, I welcome you all to the first problem solving session for numerical methods course. If you can't hear me, please let me know. I hope I'm audible to everyone. You can also use chat space to interact with me, or you can also unmute yourself. You're welcome to do anything you want. So this is like a interactive session. So please feel free to you know stop me anytime if you have any doubts, and you can ask me any questions in between. Uh, or you can also use chat space available. Okay. Um, so yeah, as I said, I welcome you all for this problem solving session. I am Ganesh Kumar. I'm a PhD student at IIT Gandhinagar. I'm a senior PhD student in the Department of Mechanical Engineering. Um, so my research actually involves using numerical methods for various fluid flow problems, especially the flow inside rockets and aircrafts. Okay, there are rocket motors and aircraft engines. Uh, we have a lot of things going on inside the engines. If you see, we have flow entering, and then combustion happening inside, and then uh, hot gases comes out, expands in the nozzle, and we generate some thrust in it. So my research involves, uh, trying to develop numerical methods, trying to develop a you computational framework such that I can resolve all these processes. So that is where the numerical methods helps me uh, in my research. And in fact, this is not the only places where you will find numerical methods. Is mechanical engineering is one space. There is a in electrical engineering you will use numerical methods. In fact, every engineering uh, discipline will require numerical methods at least at some point. Even the machine learning requires numerical methods. Even the computer science engineering. In fact, numerical methods is closely associated to computer science engineering. So um, every engineering discipline requires numerical methods at some point, and knowing numerical methods uh, is is actually uh, you know very beneficial for all the engineering disciplines. So in that way, I am really glad that you guys are taking this course, and I really hope you will enjoy it. And if you have any questions, you please let me know. I hope you guys are undergraduate students. Um, but it is free even if you are a postgraduate students, and even if you are in 11th or 12th, it should be fine. Yeah. So today what we will do is we will discuss a little bit about what we studied in week one, and we will solve few problems which would be useful for you uh, for taking assignments, okay, for week one. And we will be meeting every week till the end of this course, uh, till we will be meeting 8 times including today, every day, every Sunday from 4 to 6. Okay. So for some reason my iPad got disconnected. Please give me a second. Yes, I'm back. All right. That is from my side. And if you have any questions, or if you want to ask some questions before we start today, please let me know. Uh, yeah, I hope I'm clear. Let me check my recordings. And by the way, these sessions will also be recorded, and it will be available to you, uh, you know, in a YouTube channel. So I will upload these lectures in the YouTube channel, and I will provide you the link. You'll be able to access the link. So soon you will get an email, uh, or you can also access it through your NPTEL dashboard. Okay, that is from my side. One second. All right. So if there are no questions, maybe I will go forward and we'll discuss today's topics. So, how this session is going to go is I will give you a brief idea. So, usually I prefer recapping what we did in week one, and once we do that, I have one or two problems for you to solve. I do, and I know. I mean, I will solve with you. And if you also have a calculator, and if you can also do some problems with me, it would be really helpful for you and for me. Okay, and yeah, mostly we will be doing this. Let's say it can go till 1 hour or 1.5 hours from 4 to 5, 5:30, and after that till from 5 or 5:30, you are free to ask any questions. I will be available till 6. Okay, to ask any questions. Um, yeah, so this is how this session is. I'm going to structure this session, and yeah, okay. All right. I hope there are no questions, and maybe I will go forward with the week one's recap. Okay, my recordings are okay. All right. Um, I think we have around seven seven students here. Yeah, please feel free to stop me anytime. This is not like I'm giving the lecture. This is it's a two-way communication. So please feel free to stop me anytime and ask any doubts if you have. You no need to reserve it to the end. And if you have any doubts that I want to address before we go into it, then also feel free to unmute yourself or use the chat. Okay. All right. Uh, let's get into week one's topic. So what we did in week one is we introduced uh, something called floating point representation initially, right? So the reason to do such thing is, see, we are studying numerical methods, and numerical methods we are going to use computer extensively. Although it is not necessary to know any programming at this point for this course. Usually we introduce methods in this course, but if you can parallelly, work with computers, and if you are going to do that, then you need to have some perspective of what is this floating point numbers, how computer represents it, and what is the drawbacks of rounding off at some point. All those things we need to know. So that is why we initially give an introduction of how the number is represented in the computer. In this case, it's represented as a floating point, and uh, so usually we cannot store, like, let's say if it is 1/3, we know the 3 is going to be repeated infinite times, right? So it's an irrational number. So at some point we need to round off. So we do some round off. So in computers, in the classes we usually round off till 4 decimals. Okay, so that is what is going to happen. But in computers, let's say you take a single precision, it can go to up to 16 or 17 decimal places, if I'm not wrong. And if you go for a double precision, it will go to, I guess, around 34 or 35 decimal places. Okay, so um, but in classes we cannot, since we'll be using pen and paper to solve such problems, we cannot uh, use 17 digits. So that is the reason we'll be focusing more like 4 decimal places. But when you do such a thing, when round off to 4 decimal places or any n decimal places, uh, uh, there is going to be a round off error. Okay, so the round off, it will also be very clear when I solve today's problem. So I picked a problem in such a way to show you how the round off error varies with different methods. Okay, so initially we started with a floating point representation. So we always represent any number in this form, where m is a mantissa and 10 power k is an integer. So we represent it as in a scientific format, and uh, computers also represent it like that. And any number can be represented in this format. So And the digits in Mentissa are called significant digits. That also we learn. And uh, we also saw some rounding off uh, rules. I guess everyone knows by this time. Uh, my voice is cutting. Okay. So is everyone facing the same problem? Uh, how about now? Is it fine, or is there still a problem? Um, okay. So I hope now everyone is able to hear, right? I have just updated my microphone. All right. Were you guys able to hear me properly now? Can someone address it at the chat, or can someone speak up? All right. Thank you, Lakshmi. Um, yeah. Uh, so we all know what are the rounding of rules. I'm not going to get into details. So if it's going to be even, we will just leave it like that. If it is going to be odd, we will round off. Only if the trailing digit is 5, right? And we also introduced that errors can propagate, and we kind of saw that in one or two problems that professor solved in the lectures. We will see that more in today. And this error, when you truncate the digits, that is what we call it as a truncation error. And there is a more formal definition. If you are aware of Taylor series, you can understand it. So basically, any number can be represented as a Taylor series representation from from x naught, as from some number, right? And whenever you cut the whenever you ignore the higher order terms, uh, then that is called as truncation error. So but you don't need to worry much about it. But if you're aware of Taylor series expansion and how we use it, whenever we ignore the higher order terms, that is the error caused due to that ignoring the higher order terms is called as truncation error. Okay. Or in other way, Taylor series is an infinite series, and only we used to take only a finite number of terms, because you cannot computing infinite uh, terms in the Taylor series. So whenever you truncate it to a finite number of terms, the remaining error which is going to occur due to this infinite number of terms is going to be called as a truncation error. So that is like more formal definition, but you no need to worry. So when you truncate it, you're going to get truncation error. That is a big picture here. And then we saw something called significant digits, and we introduced more formally with this kind of setup. But yeah, I hope everyone can understand it. And then we came to linear system. So this linear system, the reason why we study is the every problem that you face in even in engineering or in physics, um, every physical representation of the real world can be expressed in terms of some equations, but those equations will be non-linear, highly it will be differential, non-linear, coupled, and very highly complex equation. And in order to solve them, what we do is we divide the domain into small segments, and then we try to write equation for each and every segment. And then uh, when you write that equation, we will end up having a bunch of linear equations. So any problem in the physics or in engineering, it's going to, let's say you take a finite element analysis or CFD, or you know uh, any problem in that case, will reduce down to a bunch of system of equation. And we are going to solve the system of equation using numerical methods. Okay. So it will be like you have like n um, equations here, and you have n variables, x1 to xn, and we need to solve it. So you can represent it like ax equal to b in a nice short compact matrix form. And you can there are different methods of solving it. One is direct method, one other is iterative method. The direct method is a Gaussian elimination method, and we saw how we have to do. And we introduced a concept called partial pivoting in order to reduce the round off errors. So Gaussian elimination also have some round off errors when you are truncating your terms only with 4 decimals. Okay. But in real scenario, in the computers, you don't truncate in 4 decimals, you truncate it at 17th decimal, right? So there it is fine for most of the practical applications. But when you do it by your own, let's say you're solving it by hand, and when you have 4 decimal places, you're going to have truncation error. And in order to reduce that, we introduce something called partial pivoting. And also we introduced the other system called ill conditioning of the system. So the system is nothing but the set of equations that you have, and you will be able to solve this equation set only if it is well conditioned. You can use these methods to solve it. So when I say solve, I mean obtaining x1 x2 to xn. Okay, from given a and b are known, we need to get x. And that can be obtained only if it is a well conditioned. Okay, if it is ill conditioned, it is going to be difficult. So how do I find whether the system is well conditioned or ill conditioned? Is based on getting a norm. And there is something called condition number based on the A matrix. So if you find this condition number to be very large, then it is going to be a ill conditioned system. And if the condition number is low, it's going to be it is a well behaved system or well conditioned system, which you can potentially solve using the methods that we discuss. Okay. And yeah, so for that you need to find the norm, and there are different norms you can use that. And I hope you must have gone through the lectures. uh, and basically this condition number, it just tells that whether a small change in any elements in A or B is going to change your solution substantially. Like, let's say let's say I give a small perturbation in A and B. Okay. And how does the solution change? The solution changes very drastically, it is going to be a yield condition system. Then that kind of system cannot be solved using these methods. Okay. And the next one we saw was LU decomposition. LU decomposition, if you look at it, the amount of computation that you need to do compared to Gauss elimination is more, right? For LU decomposition, you need to find L matrix, you need to find U matrix, and then using U and L, you need to find Z matrix or Z vector. So basically, you have AX equal to B, and you're trying to decompose this A matrix into L and U, and then you're solving two set of equation, Ux equal to Z and Lz equal to B. So first you need to find L and U, and then you need to find Z, and after you find the Z, you can find X basically. So that is like a multi-step process. But LU decomposition comes in handy when you have multiple system. For example, you have AX equal to B, or let me write it down like this. Let's say you have one system where AX equal to B1, and let's say you have another system AX equal to B2 and AX equal to B3. So now your coefficient matrix A is going to remain same for all three systems. So if you do Gauss elimination, you have to Gauss elimination is based on getting an augmented matrix AB1, AB2, AB3, and then you need to do all the row operations, and then you need to get a row echelon form. So this has to be repeated for each system, right? But in LU decomposition, you take the A, decompose L and U, and then the remaining step is going to be getting Z and then getting X, right? That will be different for each and every system. So your A matrix is already decomposed. So that is the advantage the LU decomposition provides. So You can use the LU decomposition method only if your system, only if you have something like this, ax equal to b1, ax equal to b2, like only the right hand side vector keeps on changing. Okay, so when you have such a system, then you can basically use LU decomposition, which basically improves your computation time. So or you can finish your computations in a faster manner. So that is the whole point of this LU decomposition. If not, Gauss elimination is much faster method than LU decomposition. Okay, please keep that in mind. So that's what, in a way, we decompose lower and upper triangular matrix, and then we try to find the x vector. Okay, and we also, it is also used to find the inverse of the matrix, and it is very easy when you have a triangular matrix to find the inverse. Okay, so but the condition is it has to be positive definite, and the positive definite matrix condition is something like this. Okay, um, and then there's also something called Cholesky method, and this is a bit advanced method, but similar, only if, but these are for special cases. There's something called asymmetric and positive and definite, then you can use this Cholesky method. Yeah, so these are all direct methods. You just have the you know A matrix and B matrix, you just solve them, that's it. Now there are something called iterative methods, which like you guess some value initially for x, and then you keep on changing that x until you reach a final value. Those are called iterative methods. And iterative methods are very beneficial when you have like very large matrix. So usually in the uh, classes, we usually solve like 3 by 3 matrix, right? But in real systems, that's not the case. For example, let's say you are doing a fluid flow problem, or let's say, for example, you're doing a physics related problem. Let's say formation of what do you call stars. Okay, for example. Now what you have is you have magnets, you have magnetic field, you have electrostatic field or electromagnetic things going on, you have fluid system, the flow of various dust particles, all these things you need to solve for. And what you will have is you have a very large matrix, let's say like 100 million cells. Okay, so now if you go with direct method, you are going to take enormous amount of time to solve such a system. However, if you go an iterative method, you start with some initial condition. So the initial condition, you can say something like from the boundary conditions, certain values, and you can start populate some values in between, and then you do start doing iterations. And these iterative methods are highly parallelizable. So you can do this iteration, and you can potentially save a lot of time by choosing an iterative method only. So it is only good for very large and sparse matrix. Okay, and the way that we do is there are two methods. One is Jacobi and other is Gauss Seidel. In Jacobi, we keep changing the so we change the x vector only uh, after each iteration. But in Gauss Seidel, as soon as a new value, updated value is obtained, you keep updating each and every value for the subsequent equations. Okay, so that is the difference between Jacobi and Gauss Seidel. So whenever the new updated value is available, if you use them for your next immediate calculation, then that is going to be Gauss Seidel. And if you're telling no, I do not want to do that, I want to have an initial, this is my initial condition or initial guess value, and using that, if I'm going to predict the new iteration value, and then I will change, and then I keep on doing that, then that becomes a Jacobi method. Okay, that's the difference between Jacobi and Gauss Seidel. And there's also other thing called over relaxation method, because these iterative methods takes a lot of time to converge. I mean, it's relatively faster than Gauss elimination, but it might take a lot of iteration to converge. So if you want to speed up that process, you do some successive over relaxation, which means you update these values with some additional weightage. Okay, and this is more into a mathematical way of representing it. And if it is omega is greater than 1, it's an over relaxation. If it is less than 1, it means under relaxation. So over relaxation means you are accelerating towards the convergence. Under relaxation means you are you are slowing down a bit, you are letting the matrix to stabilize. So under relaxation will be useful when you have when you have diverging systems. If you have some systems which can easily diverge, then you use under relaxation to control its divergence. But if the system is going to converge anyway, then you can do some over relaxation to speed up that process. So those are the two ways: over relaxation and under relaxation. And so for the iterative method, the important thing is you need to make sure the matrix is diagonally dominant. And only if it is diagonally dominant, we can guarantee convergence for iterative method. So for example, a matrix which is not diagonally dominant can be actually solved by direct methods like Gauss elimination or other methods, LU decomposition, anything. But it cannot be solved using iterative methods, or it is difficult to solve. You may need to adjust the over relaxation, under relaxation factors to get a closed solution, and it is also not guaranteed. So in order to guarantee convergence, diagonally dominant matrix should be A matrix should be diagonally dominant. Okay, that is an important condition. In addition, we also have more mathematical way of expressing is the eigenvalue should be any of the eigenvalues should be less than 1, or in spectral radius should be less than 1. Those are necessary and sufficient condition for convergence. Okay. So this is where we stop, and the next week is going to be, these are all linear equations. So next week it's going to be non-linear equation. We'll deal with that in next week. Okay. So I hope that is clear. If yes, I will go forward with today's problem that I have. So I have like so by the way, I hope things are clear till now. If there are any doubts, please let me know. Please stop me at any time. There's no problem with that. So what we are going to do is, I saw your assignment. It involves doing some Gauss elimination, some LU decomposition, and also Gauss Seidel iterations. So I thought I will solve you one problem in front of you, and if you have any doubts, you can ask me, so that it will be easier for you to solve your assignment problems. And assignment problems, trust me, it is easier than what I'm going to show here. So it should be possible for you to solve. Okay. All right. So today's so I have a system of equation. Of course, it's a three unknown equation. Three unknown and three there are three unknowns, and we have three equations. So it's a closed system, and so we can solve them. So that is what I have. So basically, I'm going to have a coefficient matrix which is 3 by 3. Okay. So this is my equation, and I'm going to solve using Gauss elimination with partial pivoting, and also LU decomposition, and also using Gauss Seidel method. Okay. So we will try to finish this in another 1 hour or so. And if we have time later, maybe we can try uh, programming them in MATLAB and C. Okay. MATLAB, or even in Python, whichever is. I usually go with MATLAB, but if you guys want to want me to do something in Python, you can also let me know. Yeah. All right. So yeah, basically we have these three equations, and now let's initially try to solve this equation. By solving, I mean so Chirag is asking, can you please tell how to calculate condition number? Okay. So the condition number is basically, you need to calculate the norm of where is it? Yeah. So basically, you need to calculate the norm of coefficient matrix. So you need to find the coefficient matrix, and you should calculate the norm. And you invert the coefficient matrix, you calculate its norm. So multiplication of that is going to be your condition. Okay. So this norm can be anything. It can be uh, you know induced matrix norm, matrix row norm, or a Euclidean norm. It is fine. Okay. All right. I hope that is fine. And I think you can also refer to the lecture. I remember professor solving it and showing you the condition number. If not, let me know. I can also bring up example to solve and show you the condition. All right, let's get into the Gauss elimination method. So the first method is going to be Gauss elimination. So let's first write down the A and B matrix here. So you have three equations, right? So um, so we are trying to write this in like Ax equal to B. Okay. Now x is this x vector is nothing but your x, y, and z. Okay. Now if you want to write this A matrix, then it is going to be just the coefficient of x, y, and z in that order. So 0.03, 1.24, 2.31, 1.45, 3.17, 0.98, 2.22, 1.38, 4.56. Okay. And similarly, we have a B matrix, which is going to be your right hand side, which is 4.55, 7.89, and 12.34. Okay. So it's just I wrote the same equation in terms of yeah, Chirag. I can show you by solving a problem for condition number. Uh, maybe after these, uh, maybe I will take a 2 cross 2 because 3 cross 3 is a little bit bigger. So I will take a 2 cross 2 and I will solve it once we complete this equation. I'll like once we complete this problem. Okay. All right. So the Gauss elimination. Um, the first thing we have to do is we need to get a augmented matrix. So the idea is do a row operations to eliminate uh, certain elements or to make it zero certain elements in your matrix, so that finally you will get a row echelon form. Okay. So the row echelon form is nothing but you will have 0 here, you will have 0 here, and you will have 0. So this is your row echelon form. Okay. So we need to do some row operations in an augmented matrix. So first let's write down the augmented matrix. So which is going to be A, B, 3.17, 0.98. So usually I go a little slow at this, while explaining the methods. But if you are very comfortable with the method and you know how to solve them, please go ahead and solve them, and we will finally check how my results and your results are matching. Okay. So although this is like it might feel like it is easier for some of you, but uh, just to keep everyone on the same page, I would explain each and every step in detail here. So this is how we write the augmented matrix. We just club the A and B, and we are interested in getting 0, 0, and 0 here. But we cannot just directly change those elements to 0. We need to do some row operations. We need to come up with the various ways in such a way that we can, uh, you know, uh, get 0, get the row echelon form. Okay, that is the idea. And we are going to use partial pivoting methodology also in this place. So usually partial pivoting, we know, to reduce the round off errors, we do partial pivoting, and here also we are going to do that. So in partial pivoting methodology, what is the first step? The first step is going to be to find the maximum element in the first column, and swap the. So the first step is going to be pivoting. Find maximum elements, find the you know absolute maximum, find absolute maximum in the first column, and swap them. So this is just to make the highest absolute maximum to come at the top. Okay, so in that way, if you see the this one over here, R3 is the has the absolute maximum. 2.22 is the highest. So what we will do is we will try to exchange R3, and the least is R1, so we will exchange R3 and R1. So this methodology actually reduces the. I mean, this you will have to continue doing once you eliminate the first in what do you call the elements in the first column. Once you eliminate all the elements in the first column, okay, after doing the row operation. So basically, the pivoting is done for every column wise operations. So now initially we are going to make these two elements to be 0, and before that we do the pivoting so that the maximum element in the first row comes up. So once you do that, your resulting matrix would look something like this. So you have 2.22, 1.38, and 4.56, and 12.34. So you have to swap the entire elements in the row to the top, and keep the second row as it is. There is no problem. 0.98 and 7.89, and the third row is going to be now our first row. 1.24, 2.31, 4.55. Okay, so which means I'm just rearranging the equation. So basically, if I put this equation on the top and put this equation on the bottom, that is what I'm doing. So it doesn't matter in which order you solve the equation, but at the end you will be getting x, y, and z. So it doesn't matter. Okay, now we will do some row operations. So what are the row operations that we can do? So we need to make, let's say we'll start from 3. So from row 3. So let's say we need to make before doing that, let's do one more step. So what we will do is, this is our pivot element 2.22, right? Now we will make this element to be 1, okay, which means we will take R1 and we will divide the entire R1 with the pivot element, which is 2.22. So what that would give? So it will be 1 here, there's no problem. Here it will be 1.38 divided by 2.22. Here it will be 4.56 divided by 2.22. Here it will be 12.34 divided by 2.2. Okay. The other elements will remain same: 1.45, 3.17, 0.98, 7.8. Now, you might use some calculators to get these values, but be careful, you have to round it off to 4 decimal places for every calculation. Okay, because let's say you build a computer, and if that computer cannot store 17 decimal like we have presently, but it can store only 4 decimal, so you should think in that terms. And if that is the case, every operations that you do, you will have to round it off to just 4 decimals. Okay, now if you do that thing here, and for your assignment also, it was asked to round it off to 4 decimals, so please be careful on that. So if I do these operations here, 1.38 divided by 2.22, so this comes out to be 0.622, and this comes out to be 2.054, and this comes out to be 5.558. Okay, if I make any mistakes in this, please let me know. Okay, now what we have to do, we just need to we need to make this element to be 0. We need to do some row operation to make this element to be 0. Okay, so always you have to do row operations. Okay, now, so we need to make the first element in the row 3 to be 0. If that is the case, we need to do some operation on row 3, and that is going to be, let's say you subtract it with 0.03 times r1, because the r1's first element is 1, so you multiply that with 0.033 and then you subtract them, then this becomes 0. Then if you do the same thing to everything, you multiply 0.03 to this and then you subtract them with this. Similarly, you multiply 0.023 and subtract, multiply 0.023 and subtract this. Okay, then that will give you your matrix to be how that will look. So the first row will remain same, 0.622, 2.054, 5.558, and second row is 1.45, 3.17, 0.98, and 7.89. There is no change. So but the third row, it will be like 0.03 minus 0.03, so it's going to be 0. This is going to be 0.622 into 0.03 minus, sorry, 1.24 minus this whole thing. Okay, so if you do that operation, how much is this coming to? So you can use your calculator, but remember to round it up. Okay, so now if you do this, it comes out to be 1.221, and this one will be 2.31 minus 0.03 into 2.054. So if you do this one, comes out to be 2.248, and similarly 4.55 minus 0.03 into 5.558 will come out to be 4.38. Okay, maybe I will also write this. Okay, this is fine. Now let's try to eliminate this element here. So some example will also try. Okay, sure, Lakshmi. I would also, today I do not have example, and I'm also not sure whether I will be able to complete everything. You can continue doing these calculations at home, but from next class I will come up with a few more examples for you to practice, which you can do at your home. Okay, I really appreciate it. Thank you very much. All right, so the next thing is we need to make this 0. Okay, So if that is the case, what we have to do, we have to work on row 2, do some operation on row 2, and you have row 2 minus, again you take this 1.45 multiplied by R1. So this actually makes it easier. That's why I initially, divided by 2.22, because it will take a lot of, uh, you know, thinking. So this will be much easier. Yeah. I think you mean to say is 1.45, right? Instead of 0.45. All right. So if we do this operation, let's try to replace here. So this is going to be 1.45 minus 1.45, right? And this becomes 0. This becomes minus 1.45 into 0.622. This also means minus 1.45 times 2.054. This also becomes minus 5.558 times 1.45. Okay. You can do this calculation. I think someone raised hands. Hassan, Fatima, do you want to ask any questions? By the way, you don't need to raise hands. You can just unmute and ask. So that is totally fine. Fatima, I think you were on mute. Uh, if you have any questions, please unmute yourself. So, calculator in exam usually no. You no need to carry the calculator. Instead, there will be a uh, computer. There will be calculator in the screen itself. So you will be taking computer-based test, and the calculator will already be available on your screen. Okay, you should use your mouse to you know use that. Okay. All right. Um, let's so let's say if you do this operations, let me write down the answer. You guys can check whether this is right. So this is going to be, I guess, 2.268 and minus 1.998 minus 0.169. Okay. Now, so we are almost there. We are yet to get the row echelon form. So we got these two zeros. We just need to get this zero, right? Now, once you do these two operations in the first column, when you go to the second column, since this is a partial pivoting method, you should again check whether the maximum, what is the maximum element and where you can shift them. Okay. So, but you are once you shift it to first place, you no need to go back to the first. So for example, you should check only these two elements. You should not check this element. Okay. So this is already been updated and it has moved up. So now you have only these two set, and you want to make this element to be 0, right? So now what you have to do, you just need to check these two elements. Whichever is highest, it has to be on the top. So in this case, this is highest, so there is no need to move anything. So uh, so the pivoting condition is already satisfied. So what you just have to do is you have to just make this element to be 1 for the ease of operation. So then this becomes um, R2 divided by 2.268. Okay. Now if you perform this, what will happen? So your first row is going to remain same, 2.054, 5.558, and this is going to be 0, this is going to be 1. This is going to be 1.998 divided by 2.268 and minus 1.169 divided by 2.268. Okay. The third row is going to remain same. 221, 2.248 and 4.383. Okay. Now, let's say if you do this operation, let's say if you use calculators to get this, let me just write it down in order to save some time. This comes out to be minus 0.881 minus 0.074. Okay. Now, all right. Now what we need to do, we need to make this part 0. So if that is the case, we have to do some row operations on the row 3. That is going to be R3 minus 1.221 times R2. Okay. So basically you're using R2 to subtract R3. Now if you do this, then you can directly get the row echelon form. So let's do that. 1.0622, 2.054, 5.558. This becomes 0, 1, minus 0.881, minus 0.074. This becomes 0. This becomes 1.221 minus 1.221 times 1. Right? So this becomes basically 0. And this one is 2.248 minus 1.221 times minus 0.881. Okay, so there is a minus and inside there is another minus, so it's going to be a plus, right? So if and then the other term is going to be 4.383 minus 1.221 times minus 0.074. Okay, so now if you do this one, what will happen? If you guys have calculator, you can calculate and let me know. So this comes out to be 3.324, and this one, if you do this operations, comes out to be 4.273. Okay, so now you got the row echelon form. Okay, now so this is your A B augmented matrix. Now you can decompose it again. So now you can write it as A to be 1, 0.622, 2.054, and this will be 0, 1, minus 0.881. This is going to be 0, 0, 3.34. Okay, or I can also write it in form of Ax equal to B, and this becomes A into X, Y, Z equal to B is 5.558 minus 0.074, 4.47. Okay, so now what you can do now, it is basically straightforward, right? So you, the final step is called backward substitution. So we call it backward substitution because we are going to start from Z. Okay, from backward. So till now we were doing forward elimination. I mean, we are eliminating the these rows, basically these elements, and now we will do backward substitution. So how will you do? Initially we should start with this Z, which is 3.324 times C is equal to 4.473. Okay, this you can directly find Z to be 1.346. Okay, now the second equation is going to be Y minus 0.881 Z, which is equal to minus 0.074. Okay. Now you have already found z, so we are going to substitute them. 0.881 into 1.346, which is equal to minus 0.07. So you do this operation and you finally you can get y to be 1.11. Okay. And now we have found y and z. We're just going to substitute x. X is simply x minus plus 0.622y and plus 2.054 z, which is equal to 5.558. So now since we know y and z, you just substitute them. So that is going to be x is equal to 5.558 minus 0.622 into 1.112 minus 2.054 into 1.346. So this is going to be 2.101. Okay. So finally your solution here, this x vector, which is x, y and z, is actually 2.101, 1.112 and then 1.346. This is your final solution. Now what is the error in this? So whether this is the correct solution or not, right? So what I did was, so I tried to use MATLAB to solve the same thing, where I represented something like 17 decimals. So here we took only 4 decimals, right? So when I did that, I got a most accurate solution. It is not exact solution, but it is most accurate because it is rounded off at much larger decimal places. So this is not rounded off at or you can know it is accurate solution to the third decimal place. Okay, an accurate solution would be looks something like this. It's 2.103, 1.111 and 1.346. Okay, so you can see how close they are. So these two are so which means if it is a 3x3 matrix and if you are using 4 decimal places, you are in a good condition. So let's say we'll try to find a relative error in it. So relative error, okay, relative error is, how will you find out? So this is an accurate solution. Maybe let me represent it. How did professor represent it? Okay, we can represent it something like xa. Let me write it down like xa. Okay, now if you want to find a relative error, what you have to do, you have to first x minus xa, the absolute of x minus xa divided by xa into 100 if you want it in percentage. Okay, so let's try to do that. X minus xa divided by xa, so how will that do? So which means 2.101 minus 2.103. I'm just writing all the uh, uh, yeah, so Chirag has shared an answer 2.101, 1.069 and 1.348. So this looks fine to me. In fact, I also got similar to that, right? So if you, yeah, it looks fine to me, Chirag. Yeah. So this is going to be, so as Lakshmi correctly said, this is going to be error divided by 2.103. And similarly, you can write 1.112 minus 1.111 divided by 1.111. And similarly, you can write 1.346 minus 1.346 divided by 1.346. Okay. So basically, I am actually detailing down each and every step for you to easily understand. So usually, so this time I am doing it. Next time I will not do it. I might skip some steps. So today I am writing down all the steps. Okay. So if you do this calculation, I think it comes out to be 0.095 into 100. I forgot to do into 100. And 0.09 and then 0. It's in percentage, so it's like less than 0 point, less than 1%, okay, or less than 0.1% to be precise. So that error is totally fine to have in any numerical methods, okay, in general sense. But if you continue doing this, um, let's say you find this, so this is your initial, this is your solution. Now you are using this solution for some other thing. If you're solving that another set of equations, let's say you're solving, let's say this is your B matrix now for another set of equation. Now what happens when you solve that? There will be another error. Okay, so this error will keep propagating in the continuously for the next operations that you do. So that will cause that those error will continue to build up, and at some point it will cross the 1% or 5% error margin, and which is not desirable for any uh, predictions or for any numerical uh, approximations that you are trying to. So here what we do is we will, this error is fine. This is the error in our Gauss elimination algorithm. Now we will go forward and try to solve using LU decomposition. In LU decomposition, what we have to do is we have to decompose L and U, right? In LU decomposition. So I hope uh, there is no questions till now regarding the Gauss elimination algorithm. In If there are any questions, please let me know. Um, yeah, I think every question in the chat is answered already. All right. So we will go forward and try to do LU decomposition. Let me just first try to explain you the steps. As the name suggests, we have to decompose your A matrix into L and U. Okay. So for example, if I write the A matrix to be 0.03, 1.24, 2.31, and 1.45, 3.17, 0.98. Okay. 2.22. So here you do not do augmented matrix. So if you remember, the whole point of doing this is to eliminate the dependence of the method on B matrix. So let's say I have a multiple system of equations, and I have which varies only in the solution vector, the source vector, which is B, right? If that is the case, I want to devise a method which can efficiently solve this, then that is going to be LU decomposition. So here you do not do augmented matrix. So you just have A matrix. You have to write it in terms of L and U. Okay, so that's the simple thing. So now if you want to do that, um, so basically you have Ax equal to B. You will write A in terms of L and U. So what it will provide, LU x equal to B. Okay. So now you can write Ux to be, U is a matrix and X is a vector. Now L into Z will be equal to B. Okay. So this basically I'm going to write Ux equal to some Z, or let's say, let me write it down like something else. Let's say P. Okay. In order to remove the confusion. LP equal to B. Okay. Lakshmi is telling this topic is not covered in the lecture video. I guess I guess it has been covered. So if you look at the third lecture of week 1, it is about LU decomposition. You might have missed it, but it's fine. Uh, you can go back and revise it. Okay. I mean, you can go back and study it. Okay. So it's the third lecture. What you are basically doing is you are decomposing into L and U, and then you are trying to write this as a P, and then so you are basically having two set of system of equation. But good thing about this is L is a lower triangular matrix and U is a upper triangular matrix. So either you can do forward substitution or backward substitution to get uh, the to get P and uh, X basically. Okay, so once you get P, you substitute them, get X. Okay, but the thing is you need to find that L and U. So let's say if I want to write this L, so L can be written as L11 0 0, L21 L22 0, L31 L32 L33. This is L, and similarly you can write U. Let me move it down to here. Similarly, you can write U as U11, U12, U 13, 0 U22, U23, 0 0 U33. Okay. But the problem here is you have only so this is representing only these elements. You have 9 elements in your A matrix. Now you what you have is you have 6 over here and 6 over here, which is total 12. So there is 9 elements, and that has to represent 12 things, which is not possible to get. Okay, so that's why what we do is we either make U's to be 1 or L's to be 1. So depending, I mean, you can do either way. uh, Both are going to give you same result. Okay, so in this case what we will do is we will make these things to be 1. So we are going to take it for granted. So these things are 1. So you make this 3 1. So now what happens, you will have 6, you will have 2, total 3, which is total 9. So you have you will have these 9 elements to represent this L's and U's. Okay, now how do we find L and U? Okay. That is our next task, to find all these elements L11, L12, L21, all these elements we need to find out. That is our next task. Okay, now if you let me try to give you the perspective, then you can itself find out how you can do it. So let me write it down in terms of L and U. L11 0 0, L21, L22 0, L31, L32, L33 multiplied by U, which is 1, U12, U13, 0 1, U23, 0 0 1. So this is nothing but your A matrix, which is 0.03, 1.24, 2.31, 1.45, 3.17, 0.98, 2.22, 1.38, 4.56. Okay, so this is basically what we are trying to do. This is L, this is U, and this is nothing but A. Okay, now how do we can, so we all know the matrix multiplication, how it is done. So for example, if you take this, we have 2 zeros here, so what you can do is you can multiply this and this, which is going to give you the this element. So in that way, since we have zeros here, so this L1 can be directly obtained from 0.03. Similarly, you can do the same thing for this, which means this three elements is nothing but your A matrix elements. Okay, so this is because the way we wrote, since this is in row echelon form, and since you have uh, the vector here to be 1 0 0, so if you perform this operation, you are going to get uh, the same as in the right hand side. So that is how this is going to work. So when you took this u1 to be ui's to be 1, the first thing you have to do is you have to find first column of L. Okay, once you find this, you have to find first row of U. Okay, once you do these two, you have to find second column of L, second row of U, and then third column of L, third row of U. Okay, so this is a column of L and row of U. That is how you go in the process. So the um, first is to find first column of L, and subsequently you find first row of U. Okay, first column of L we already know, L11 is going to be 0.03, L21 is going to be 1.45, and L31 is going to be 2.22. So if you do all these things, what will happen? Let me write it down. So this is going to be 0 0 L2 2 0 L3 2 L3 3, then 1 U1 2 U1 3 0 1 U2 3 0 0 1. Okay, this is equal to 0.03, 1.24, 2.31, 1.45, 3.17, 0.98, 2.22, 1.38, 4.56. So the first column of L we found. So this is done. Now we need to find first row of U. So how is this done? So so first let's write it for U1 2. So what we can do, we can take this one and this, right? So that will give you this element. Okay, so in that way you can get u1. So basically you're trying to do some matrix multiplication in order to match them values. So here it will be 0.03 u12 plus 0 times 1, which is 0, so I'm not going to write it, is equal to 1.24. So this will give you u12, 1.24 divided by 0.03. Okay, similarly the same way you have this row and then this column. Okay, but these two are zero, so you don't need to worry about these two. So this multiplied by this is going to be give you this. So let me write it down. 0.03 u13 is equal to 2.31. Thus will give you u13 to be 2.31 divided by 0.03. All right, so if you do that, what is the answer you are getting? Since it is divided by 0.03, you're going to get some large numbers, 41.33 and 77. Okay, let's write it down again to get a fresh perspective. So you're getting 0.03 0 0 1.45 L22 0 2.22 L32 L33 and then 1 41.33 77 0 1 2 2 3 0 0 1, which is equal to A matrix. Now maybe I will write it up. 0.03 1.24 All right. So um, now we have only this. So these three, and then you have this one. So we have four more to find out. And as I said, what we have to do is we have to go column of L first. Okay, so since we have found this and we have found this, the next thing is to find these two and then to find these two. So in that one is already found, so there's no need to worry. Only you two, three you need to find out. So right, let's uh, let's do that. So this is going to be L. Let's say I'm writing it for this one. This is going to be this row and then this column. So in that we know every element except L22. Okay, 1.45 into 41.33 plus L22 is going to be the center element, which is 3.17. So from this you can get L22. And similarly L33, the same row operation, 2.22 into 41.33 plus L32 is equal to the third row, second column, 1.38. Let's if you do this, what will happen? Minus 56.76 and minus 90.37. Uh, so now we have found this. The next thing is to find U23. Okay. How will you find U23? Wait a minute. Let me write this down so that you get an idea. Okay. L22 and L32 is going to be minus 56.16 and minus 90.37. So now we need to get U23. So to get U23, we have to do, we should do this operation and this operation. That will give you 0.98. Okay. So in lectures, what you would have observed is there are some uh, the formulas are given, uh, and you can just follow that formula to do this. But this is much simpler, and you don't need to really need to remember the formula. If you write it down correctly, you can easily identify. It's just based on logic. Okay. uh, Into U23 going to be 0.98. So from here you can get U23 to be something like 1.948. Okay. And then finally we have to find L33. L33, what we have to do? 2.22 into 77 minus 90.37 into U23, which is 948, plus L33 equal to 4.56. So this will give L33 to be something like 9.66. Okay. So this is first row, first column that we did here, and here what we are doing is second row of L, sorry, second column of L, right? Second row of U. Then finally here, third column of U. And the third row of U is 1, so no need to worry about it. Alright, let's write it down separately. So here we have 56.76 minus 90.37 and then 9.66 and then 1.948. So this is your L and this is your U. So this is how you decompose L and U for a given A matrix. So now that you have decomposed, the next method is, the next step is, we know Ax equal to B. Now A is replaced by L and U. Lu x equal to B. So we know Ux equal to is P. If you write Ux equal to P, then you know Lp equal to B. So we know L, we know B. So we can find P from this. Okay. So let's try to do that. If I do that, what happens? So I can write L as 0.0300 1.45 minus 56.76 2.22 minus 90.37 9.66 times P. Let's say P1, P2, P3 equal to B is 4.55. So this is given in the question: 4.55, 7.89, 12.34. Okay. So this is, you can do this is what we call it as forward substitution. So we begin, since you have zeros here, you no need to do any row operation. You just find P1, and then from once you find P1, you can find P2, and then you can find P3. As simple as that. Okay. So let's write that down: 0.03 P1 equal to 4.55. So from here you can find P1 to be something like 151.7. Then 1.45 times 151.7 minus 56.76. P2 is equal to 7.89. So from here you can find P2 to be 3.737. And then finally, the final equation, which is 2.22 into 151.7 minus 90.37 into 3.737 plus 9.66 into P3 equal to 12.3. So from this you can find P3 to be 1.371. Okay. So this is how you find P. So once you find P, let me write it down for clarity: 3.737, 1.371. Okay. So once you know P, what happens? You know U times X is equal to P. Our ultimate aim is to get X, right? So we know U times X is equal to P. Now let's write that down. It is going to be 141.33 77 0 1 1.948 001. This is going to be X, Y, and Z. This is going to be P is 151.7, 3.737, 1.371. So, okay, P we just found, right, from LP equal to P. So now you do backward substitution. So this is forward substitution. And here you do backward substitution. Okay. So there is no need to do any row operation. Only thing is, once you decompose L and U, it is much easier. So now this gives z to be 1.371, and the second equation is y plus 1.948z, which is equal to 3.737. So from here you can get y to be how much? I'm getting something like 1.066. And then from the first equation you have x plus 41.33y plus 77z equal to 151.7, which gives x to be 2. In fact, exactly it was giving me. Okay, so now this is our x from LU decomposition, which is 2.000, y is 1.066, and z is 1.371. Okay, now let's go back and check. So this is from LU decomposition that we got. So Moksha is asking whether recording will be available. Once this session is over, I'll just upload it in the YouTube, and from your NPTEL dashboard, you will be able to access it. Okay, so there will be a problem solving sessions link, and if you open that link, there will be a Google Sheet page, and there you will be updating all the links of YouTube. Okay, links from YouTube. Let's go back. So this is our accurate solution. Let's say let me copy this. Okay, so now this is our accurate solution. Let me also let me write this as x LU decomposition. Similarly, I will also write Gauss elimination, which came out to be 1.101, 1.112, 1.346. So this was Gauss elimination, and this was LU decomposition. And you can see the error in LU decomposition is higher. Okay, and the reason is due to you must have noticed here, right? So you did a lot of operation. So whenever you do multiple operations, like any x, y, division, multiplication, addition, subtraction, whatever you do, every operation, when you do round off, when you do cut everything at the fourth decimal place, what happens is the error keeps on propagating, and that is what you see here. So the error is much more in LU decomposition because the amount of operation, the absolute number of operations that you do in LU decomposition is much higher, or it's higher compared to the Gauss elimination. And because of that, your error, if you calculate, let's try to calculate the relative error from LU decomposition. It's going to be how much? It's 2 minus 2.103 by 2.103. Okay, I'm not going to do this again, but I will just give you the number. Comes to be 4.89, 4.05, and 1.86 percentage, which means the relative error is something like 5% error. Value. But what we saw was 0.1% error for Gauss elimination. Okay, because the number of operations is lesser. Okay, so you see a lot of error, but all this is because of 4 decimal places. Doesn't mean LU decomposition is useless. In computer, it is very useful. Okay, when you are dealing with 17 digits, or double precision, if you go, it will go to 34, 35 digits. You no need to really worry about it. Okay, since by hand you cannot keep track of all the 34, 35 digits, it is showing us 5% error. Okay, all right. So I hope the solution, the methodology, you guys were able to follow. You can also do the same thing with whatever the so for example, professor must have taught you by showing you an equation like this, right? You just you can use this also, doesn't matter. Basically we did the same thing. If you want to, need to be very structured way, if you want to do it, then you can follow this, there's no problem. Or you just write it down and you can easily figure it out based on logic. Okay, so that is also a way to solve this problem. In that way, you no need to remember the formulas. That's it. Okay. Any doubts in LU decomposition or Gauss elimination? All right. We are almost towards the end of the today's session. Let me just solve the final Gauss seidel. Okay. This is an iterative method. Gauss seidel. So now, um, in Gauss seidel, as I said, uh, you do not write it as a matrix. Instead, you initially have some initial guess value, and you try to substitute these numbers in the guess value and see what would be the updated value, and whether you can, if you keep doing this again and again as an iterations, will you be able to reach the uh, what do you call, the solution. Okay, so what we have is these three equations. Let me write down the equation again. Let me go back to the equations. These are the three equations. Okay, now whenever you wanted to write Gauss seidel, whenever you want to implement a iterative method, what are you trying to do is you are trying to find one of the variable from one equation. Okay, for example, we'll take this equation and let's try to find the x from this equation. Okay, and assume that other things are known. So if you do that, you just rewrite this equation. You can just rewrite this equation like this: x is equal to 1 divided by 0.33, 4.55 minus 1.241 minus 2.313. Okay, this is the way to write it. Okay, given that, provided that you know y and z. Similarly, let's now so we will use first equation to find x, second equation to find y, and third equation to find z. So if that is the case, if you want to write y, that is going to be 1 divided by 3.17 into 7.89 minus 1.45x minus 0.98. Similarly, z, if I want to write 1 divided by 4.56, 12.34 minus 1.38y minus 2.22x. Okay, so these are the three equations, x, y, and z. So now in Gauss seidel, you will find the k plus 1 is an iteration value. You will find k plus 1 values from the kth iteration value. Okay, similarly here k plus 1 you will find from the kth iteration value. If you find it from the kth iteration value here, it is going to be Gauss Jordan, and if you find it from the newest value that you recently found, then it becomes Gaussian. So here similarly k plus 1 is coming from here, both y and x are known, so you just take k plus 1 here. So this is your entire Gauss seidel methodology. Okay, now let's try from some numbers. So for example, The more closer you are to the solution, the more easier you are going to get the value. So for it, so since we already found the solution from the previous, see, you can actually start from x of 0 is going to be some 0 0 0. Okay, you can start from 0 0 0 also, there's no problem in it. Or you can start from 1 1 1 also, there's no problem in it. Or 1 1 1, there's no problem in it. In whatever way you can start it, you can always, whether you find convergence or not, we will find it later, but you can start from any initial condition. Okay, but the closer is your initial condition to the actual solution, the quicker your convergence will. Okay, so in this case, since we already know some of the values, we can just start with let's say 2 1 1. Okay, there's no reason to not start with 2 1 1, or let's say I will start with 1 1 1 itself. You guys can start with 2 1 1 and see how it varies. So let's say if I start with 1 1 1, okay, so the first iteration would look something like this. X of 1 is going to be 1 divided by 0.33, 4.55 minus 1.24 times 1 minus 2.31 times 1. So this comes out to be something like 33.33. And then x of 2, or in this case it's y, right? So y of 1 is going to be 1 divided by 3.17, 7.89 minus 1.45 times 3.33 minus 0.98 times 1. Since we didn't find z yet, we can still use the previous iteration value. Here it is 1. Okay, this is going to be something like minus 13.07. Similarly, y at z at 1 at the first iteration is going to be 4.56, 12.34 minus 2.22 into 33.33 minus 1.38 into minus 13.07. So this will come out to be something like 9.56. Okay. So now what happened here, really here is, you have from the initial condition that you have 1 1 1, you have went to first iteration value, which is basically 33.33 minus 13.07 minus 9.564. Okay, please remember uh, your accurate solution, or your solution is somewhere in 2 1 1 range. But what happened here is, already it has went to very high values like 33, 13, 9 and all these things, right? Let's talk about this in a while. Let's move forward and we'll try to do the second iteration. Okay, so how the second iteration will look? X of 2 is going to be same thing, 1.03, the same equation. I mean the same these are the three equations, just you need to replace y and z with the new values that you have. If you do that, it becomes 455 minus 1.24 into minus 13.07 minus 2.31 times minus 9.56. Okay, so this is going to be, if you calculate it, it comes out to be 1428. Y of 2 is 1 divided by 3.17, 7.89 minus 1.45 into 1428 minus 0.98 into minus 9.564. This comes out to be minus 647.9, and then Z2 equal to 1.456 into 12.34 minus 2.22 into 1428 minus 1.38 into 647.9. This comes out to be minus 550.2. Okay, you see where this is going. Let me write it down separately so that you understand here. And then the second iteration is going to be, actually second iteration is 1428 minus 647.9 minus 550.2. Okay, this is how this is going actually. It's not like I did some mistake in calculation, but what I need is what is my accurate solution? Somewhere around 2.1, 1.1 and 1.3, correct? To be precise, it's like 103, 111, and 3.1, 1.346. This is my accurate solution. But where the iteration is going is it keeps on increasing from 33 to now it went to 14,428, and minus 13 become minus 647, minus 964, I mean 9.564 becomes 550. So if I do third iteration, what do you guys think will happen? So in the third iteration, based on this trend, this is going to keep increasing, and this is what we call it as a divergence. And so that is the problem with the Gauss-Seidel methodology. For this system, the Gauss-Seidel will not work, and the reason is the present system that you are dealing with is not diagonally dominant. So if you are trying to solve using Gauss-Seidel, the first thing you have to do before getting into iteration is check for diagonal dominance. Okay, so now check this system, check whether this is diagonally dominant or not, which means your diagonal terms, for example, these are the diagonal terms in A, right? In these diagonal terms should be greater than sum of other terms in that row. Okay, for example, let's take this row. This is the diagonal term 0.03, and if you sum 1.24 and 2.31, it comes out to be somewhere like 3.55, right? So this sum is 3.55, but this is 0.03. So this is less than this. This says this is not diagonally dominant. It's not diagonally dominant. Okay, so this is the reason this Gauss-Seidel method will not work for this. Okay, so first thing you have to check, like I did, you should not just go forward and do the iteration. You should first thing you should do is you should check whether the system is diagonally dominant or not. Okay, in this case this is not a diagonally dominant, so there is no way Gauss-Seidel will give you the results. But if you want to make it diagonally dominant, let's say I want to solve it using iterative method, what should I do? So what you can do is actually you should find out a way such that the you can move these equations around. You can swap these equations around front and back in such a way that the diagonal dominance can be achieved. But in this case, that is also not possible. The reason is, so for this case, you have 1.22 and 1.38 is less than this term. So this is perfect. There's no problem with it. So, and then similarly, if you take this, this one is greater than these two addition, right? So this is also no problem. So these two are already diagonally dominant and only one is not right. So if you rearrange, there's no way you're going to get diagonally dominance with this system. So that is the reason you cannot solve this system using Gauss-Seidel method. Okay. If these numbers are a little bit different, then you can rearrange this equation and you can achieve diagonal dominance with the system. And once you have diagonal dominance, then you go forward with the iterations. Okay. So I just want to showcase the importance of diagonal dominance here and want to show if you don't have diagonal dominance, you are not going to get a solution through Gauss-Seidel. Although this is possible, although you can get a solution through Gauss elimination or LU decomposition, Gauss-Seidel cannot give you such a solution. Okay, because of the iterative nature. You need diagonal dominance to guarantee convergence. Okay, any questions? So yeah, we cannot solve this using Gauss-Seidel. You can also try doing it. Let's say, why don't you give it a try once more? Now we started with x equal to 1, 1, 1, right? Let's say you start your x with 2, 1, 1, okay, which is closer to the accurate solution. Okay, let me write that down. Let's say if you have free time, you try to do that. This is your accurate solution, right? Take x naught and do this Gauss-Seidel and see what happens. 2, 1, 1, okay, and see what happens. So maybe I can quickly check with my MATLAB. Oh, my MATLAB is not. Oh. Okay, so this is one way, or you can also take x naught to be a little closer, 2.1, 1.1, 1.3, and see whether at least this was able to converge on. Okay, and check for yourself how it behaves. I will leave it as a suspense for you guys to find out. Okay, any questions you guys have for these three methods? I hope it is useful for you guys in solving the assignment problems. If you have any doubts, please let me know. Take some time, let's say 1 or 2 minutes. We'll try to find a problem for condition number.
Sir, can you go to the previous slides?
Which one?
In that Gauss-Seidel method.
Okay.
So in that 1 by 0.33 will come or 1 by 0.03 will come?
Oh, okay. Yeah, you are right. It should be 1.03. Yeah, but that does not change the solution because I did it with 03. You can check for yourself. Mm. Yeah. Yeah. Also, do check all the values that I show here in this class. Um, I can make some, calculation mistakes. So yeah, and it's also good idea for you guys to solve it once, so you will also feel confident about solving such problems. Lakshmi and Asana Fatima is asking for today's class notes. Yeah, yeah. So that will also be uploaded in the drive link, and this and both of them, both the recordings and the drive link, both you can access from the website. Okay, from the dashboard at NPTEL. All right. So I think long back someone asked me for condition number. I think Chirag. Chirag, are you around? Okay. Maybe I will solve one additional problem. It's a simple problem. Condition number. So let's say you have a matrix AX. A is something like, let's say I have a 2 by 2 matrix. Where is that 2 by 2? Let's say I'm going to have 1 1. And this is okay. This one. Wait a minute. 1.1, 2.1. Okay. Let's say you have matrix something like this. I hope this works. So AX equal to B. If this does not work, I will find another problem and I will add them with this notes and I will send it to you so that it will be useful for you guys. But I will show you what is the methodology. So AX equal to B, but it is represented by 2 cross 2 matrix, and A is, these are the numbers, and B, these are the numbers. Okay. Now I want to find whether the system is well behaved, or whether it is well conditioned or ill conditioned. Okay. So one thing that you can blindly do is check for condition number. So what is the condition number? You can write it as condition of A. Actually, this is also available in MATLAB. If you are interested, you are free to look at try to do it in MATLAB. But we will do it by hand here. So the condition A is nothing but the norm of A, the norm of A inverse. Okay, clear? Now, the norm of A, we saw there are different norms. Let's go forward with one of the norm. Where is it? Yeah, here. So let's say we go forward with the maximum row norm. Okay. There also should be one more norm, right? Mm, just give me a minute. Maximum row norm. Let me just copy this. And you can repeat the same thing with the other norms. Okay. So now let's try to do it. So how do you write the norm of A now? So summation of j equal to 1 to n aij. So which means 1 plus this maximum of the first I is row, j is column, right? It will be 1 plus 1.1 comma 1.1 plus 1. Okay, so this is going to be 1 plus 1.1 is 2.1, 2.1 comma 2.1, so both are 2, so it's going to be 2.1. This is your norm of A. Now similarly you do A inverse. What is A inverse for 2 by 2 matrix? A inverse of this matrix is going to be simply 1 1 minus 1.1 minus 1.1, right? And you should also do 1 by determinant of A, right? What is the determinant of A? 1 minus 1.1 times 1.1. 1 minus 1.1 times 1 minus 0.21. So this comes out to be 1 divided by, so minus 4.76, 1 minus 1.1 minus 1.1. So if I do any mistakes, please let me know. Minus 4.76 times 1.1, which is 5.238, 5.238, 1. Okay. So now you find the norm of A inverse. How will that look? Maximum of, oh sorry, this is supposed to be minus 4.76. So maximum of minus 4.76 plus 5.238, minus 4.76 plus, okay, I took a, symmetric system, so the maximum is I think minus 0.21. Which one is, what are you talking about? What is minus 0.21? Oh, determinant. Okay, determinant is 1 minus 1.1. Oh sorry, 1.1 times 1.1. Oh sorry, yeah, 0.21. Sorry about the mistake.
Sir, I think 4.76 is correct only because determinant is 0.21 and 1 divided by 0.21 is 4.76 only.
Oh, okay,
So
okay.
minus 4.76 is correct.
Oh, yeah. Sorry, I was right. Yeah, guys, please check Chirag and Lakshmi. All right. So if this is the case, what is the what is this you're getting? 4.76 plus 5.238. How much is it? This comes out to be something like 9.998. Okay. So your condition number is, how will you write? It's nothing but 2.1 times 9.998. Okay, into 2.1. This comes out to be 20.996. So this is how you find the condition number. So now 20.996 is still okay. Now let's say you take a such that you have 1.001, let's say 401, and another this one 1.0001 and 1. Okay, now you find the condition number for this. Okay, and let's see, let me also try to do it. So how how much will this one? So this will have condition number to be 2.001. I mean norm should be 2.001, and A inverse is going to be 1.00101 square 1 minus 1 divided by S minus 4999.75 times 1 minus 1.0001 minus 1.0001 and 1. Okay. Now if you do norm of this is going to be max of, so I'm skipping few steps here, minus 4999.75 plus 101, which is 5.000 5000.25 plus not plus the same thing, minus 499.75 plus 500.25. Okay, this is 499.75 499.75 plus 5000.25 comes out to be 10,000. So roughly I think it may have some digits after this, but 10,000. And the condition number for this A, let me call this A2, okay, to not avoid confusion. A2, A2, this is coming out to be some 10,000 times 2.001, which is 20,000, right? I don't know why I'm calculating this with calculator. 20,001. Okay, so look at the condition number of A. Condition number of A was 20.1, while the condition number of A2 was 20,000. So whenever your condition number is this large, around in thousands, there's no way it is actually yield condition system. So this is an yield condition system. Okay, is that clear how to find the condition number? And for a 2 by 2 matrix, it should be clear, right? Is there any questions on this? So what this condition number mean is, so when you have a very high condition number like this, for any small change in, let's say, B from 2.1, let's say if I change it to 2.00 2.101, for this small change you are going to have a larger difference in xy, okay, your solution. So if that is the case, that will happen in a ill condition system, and it is also sometimes difficult to solve the ill condition system. So that's why you find a condition number once you find a matrix and see whether there is a possibility of ill condition matrix that you have found. Okay, is that clear how to find norm and find the condition number, or do you have any further questions? Chirag and Chirag, I think Chirag was asking the question, right? Yeah. Okay, you guys want my email ID, all right? I will share you my email ID over the chat. Yeah, this is my email ID. If you have any doubts, you can contact me. But I might be a little busy for coming 2-3 weeks. After that, I should be able to easily reply to your email. All right. Any questions? Sorry, I had to cross over 6 o'clock. But if you have any questions, please feel free to stay back and ask, I can stay for another 5 minutes. If not, we will meet next week with few more questions related to nonlinear equations. I hope this is helpful for your assignment for this week. Okay. All right. Good evening. Thank you. All right. Uh, Damodaran, I muted you. Do you have any questions? If you have any questions, please let me know. Feel free to unmute.
Nothing, sir. I just want to say thank you for
Sure,
excellent
sure.
presentation.
Sure. No problem.
Thank you.
Thank you. Thanks for attending.
Thank you, sir.
All right. Karishma is asking. Yeah. So I have uploaded in the drive. I will share you the link. Um, so I hope you guys know how to do this. So you can go to the. Not sure I'm logged in here. Let me just quickly show you how to do this. Oh my God. So if you go to the course page, um, you can. Okay, so it is not available right now, I guess. Week one. Let's say I'm going to quiz. Download videos. Okay, so here you see week one, week two, right? So after this download videos, there will be additionally problem solving sessions coming here. Okay, soon NPTEL will share you the updates. So there, if you open that, there will be a link, the Google Sheets link, where you can access both recordings of video and also uh, the notes. Okay, you should be getting in maybe a couple of days. Okay, don't worry. All right. If there are no more questions, thanks for attending. We'll see you in next week.